Hey, everyone, welcome back to the channel. Today we're diving into something extraordinary happening 93 million miles away from us. The sun's magnetic field is about to flip. That's right, a massive cosmic event is underway, and it could have some surprising consequences for life here on Earth. So what exactly does it mean when the sun's magnetic field flips? Why does it happen? And is it something we should be worried about? Stick around because we're about to break it all down for you. Exciting changes are happening with the sun. Recently, it's been a hot topic, and now it's gearing up for a major shift. Its magnetic field is about to flip. This event happens regularly during the midpoint of the solar cycle, but it's no small matter. It has significant consequences for us here on Earth. Why should we care? This flip could bring along some serious risks, potentially causing major disruptions or even disasters across the globe. But what exactly is going on with our sun? The sun's magnetic field is generated by the movement of electrically charged gases within it, a process known as the solar dynamo. Over time, this magnetic field becomes increasingly complex, twisting and changing shape due to the sun's intense activity. Eventually, this chaotic dance of energy leads to a complete reversal of its magnetic poles. In other words, the sun's north magnetic pole becomes the south, and vice versa. Now let's dive a little deeper into the sun's structure. The sun is primarily made up of hydrogen and helium in a special state called plasma. In this state, electrons are no longer bound to atoms, creating a mix of free electrons and ions. The sun's interior is divided into several layers, with the core at the very center. Surrounding the core are the radiative zone and the convective zone. The core is where nuclear fusion takes place, turning hydrogen into helium and releasing an enormous amount of energy. The core of the sun isn't just a fiery center. It's surrounded by fascinating layers that play a critical role in how energy moves outward. One of these layers is called the radiative zone, where energy travels incredibly slowly as photons are absorbed and re-emitted by the solar plasma. It's a gradual and complex journey. Moving outward, we reach the convective zone, where things get a little more dynamic. Here, energy is transferred by convection. Hot plasma rises to the surface, cools down, and then sinks back, creating powerful currents. But it's not just about heat transfer. This is where the magic happens. The solar dynamo, the process that generates the sun's magnetic field, takes place mainly in the convective zone and a thin, crucial layer called the tachocline. This thin boundary between the radiative and convective zones is where the sun's rotation and flow patterns work together to generate its magnetic field. And here's something really interesting. The sun doesn't rotate like a solid object. Its different parts rotate at different speeds, with the equator spinning faster than the poles. This phenomenon, known as differential rotation, stretches and twists the sun's magnetic field lines, adding even more complexity to the mix. This all ties into the solar cycle, which lasts about 11 years. Throughout this cycle, the sun's magnetic field undergoes dramatic changes, eventually leading to a reversal of the magnetic poles. The cycle begins at solar minimum, a phase with few sunspots and low solar activity. During this time, the magnetic field is relatively simple, with clear north and south poles. But as the cycle progresses, things heat up. As the solar cycle progresses, sunspots begin to increase. These dark spots on the sun's surface are areas of intense magnetic activity, signaling that something powerful is happening beneath the surface. They usually appear in pairs, each with opposite magnetic charges, and gradually drift toward the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity. During this time, we see the highest number of sunspots, as well as intense solar flares and coronal mass ejections, CMEs, which hurl huge amounts of charged particles into space. The sun's magnetic field becomes incredibly complex and tangled during this phase, leading to dramatic bursts of energy. As the solar maximum fades, the sun's magnetic field begins to untangle itself. Magnetic field lines reconnect, and and the sun's global magnetic field gradually flips its polarity. The North Pole becomes the south, and the south becomes the north. This incredible transformation is driven by the movement of the sun's plasma, a process that continues until the flip is complete. After the pole reversal, the sun enters a phase of lower activity, returning to solar minimum. At this point, the magnetic field is more organized, and the sun prepares for the next cycle to begin. Right now, we're in the solar maximum stage, and the sun's magnetic field is on the verge of flipping once again. While this brings fascinating changes, it also comes with the potential for dangerous solar activity. But don't worry, this magnetic field reversal is a natural part of the sun's ongoing cycle. As the solar cycle progresses, the sun's magnetic field undergoes dramatic changes, becoming increasingly twisted and complex. Right now, it's at its most chaotic state, which means it's getting ready for a major event, the magnetic field flip. But when exactly will this happen? Scientists are constantly monitoring the sun's activity using a variety of advanced instruments. Observatories equipped with powerful telescopes on Earth and in space provide us with detailed images of the sun's surface, allowing us to keep a close eye on sunspots. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, ESDO, give us crucial insights by measuring changes in the sun's magnetic field over time. One major clue that a magnetic field flip is coming? Sunspots. During solar maximum, sunspots appear more frequently and become more prominent. As they move toward the sun's equator, they signal that the magnetic field is becoming unstable and is on the verge of reversing. Now, let's dig a little deeper into the role of these sunspots. They form when the sun's magnetic field lines twist and tangle. A result of differential rotation, the equator spins faster than the poles, stretching and bending the magnetic lines. When these lines loop and twist enough, sunspots emerge on the surface, marking areas of intense magnetic activity. Sunspots are fascinating features on the sun's surface, created when magnetic activity blocks the upward movement of hot plasma. This process leads to the formation of cooler, darker areas that we see as sunspots. But these intriguing spots aren't just for show. They can trigger powerful solar flares and coronal mass ejections, CMEs, that release vast amounts of energy and charged particles into space. When directed toward Earth, these events can disrupt satellite communications, affect power grids, and pose serious risks to astronauts in space. While increased solar activity can create stunning auroras in our atmosphere, it can also raise radiation levels in the upper atmosphere, making it a double-edged sword. It's important to note that solar flares and CMEs, while related, are not the same thing. Solar flares are sudden and intense bursts of energy caused by the release of magnetic energy associated with sunspots. Imagine them as bright explosions on the sun's surface, emitting a tremendous amount of energy and light, often in the form of X-rays and ultraviolet radiation. On the other hand, coronal mass ejections, CMEs, are massive releases of solar wind and magnetic fields from the sun's corona. You can think of them as enormous bubbles of gas and magnetic fields being expelled into space. When a CME occurs, it sends billions of tons of solar particles racing into space at incredible speeds. So, while solar flares and CMEs are distinct phenomena, they both originate from the sun's magnetic activity and can have profound effects on our planet. While solar flares and coronal mass ejections, CMEs, are related phenomena, they are not identical. A solar flare can occur on its own, but sometimes a particularly powerful flare is accompanied by a CME. Solar flares can disrupt radio communications and navigation signals, posing significant risks to astronauts in space. However, CMEs tend to have broader impacts. They can trigger geomagnetic storms that disrupt power grids, satellite operations, and navigation systems. While they can enhance beautiful auroras, they also present serious risks to Earth's technology and infrastructure. Another crucial factor to consider is that during periods of heightened solar activity, the amount of harmful radiation reaching Earth also increases. Satellites and other spacecraft are especially vulnerable to this increased solar activity. Charged particles emitted by the sun can damage electronic components, disrupt communication signals, and even alter satellite trajectories. Although the sun's magnetic field reversal doesn't directly influence Earth's atmosphere, the associated changes in solar activity can have important implications. Some research suggests that fluctuations in solar radiation may affect atmospheric conditions and weather systems. For instance, heightened solar activity could lead to slight variations in our weather patterns, showcasing just how interconnected our world is with the sun's behavior. When we talk about the warming of Earth's atmosphere, a critical topic in climate change discussions, we often wonder, could the beautiful auroras be the only silver lining from these solar fluctuations? One of the most striking results of intensified solar activity is the enhancement of these breathtaking natural light displays, known as the northern and southern lights. Auroras are created when charged particles from the sun collide with Earth's magnetic field and atmosphere. The aurora borealis, or northern lights, is the most famous, but these stunning displays are also visible near the South Pole during periods of high solar activity. When the sun's energy peaks, auroras become more frequent and can even be seen at lower latitudes, turning evening skies into vibrant shows of color. However, while these magnificent lights are captivating, there are also serious concerns tied to the sun's magnetic reversal. If we aren't adequately prepared, one major risk is the increased likelihood of geomagnetic storms. These storms happen when solar winds filled with charged particles interact with Earth's magnetic field. In extreme cases, they can lead to widespread blackouts and damage to critical infrastructure. One notable historical event to consider is the Carrington event of 1859, a powerful solar storm that caused telegraph systems to fail and illuminated the skies with brilliant auroras as far south as Hawaii. As we face a future with fluctuating solar activity, it's essential to balance our appreciation for the beauty of auroras with a readiness to address the potential risks they bring. On September 1 Est, 1859, a remarkable event unfolded that would go down in history as the Carrington event. Astronomer Richard Carrington was observing the sun when he noticed a brilliant flash of light bursting from a cluster of sunspots. This extraordinary phenomenon marked the most significant geomagnetic storm ever documented. The flash Carrington observed was actually an immense solar flare, a powerful surge of energy released from the sun's magnetic field. This flare was so intense that it triggered a massive coronal mass ejection, CME aimed directly at Earth. In an astonishing feat of speed, the CME reached our planet in just 17.6 hours, a remarkable duration considering the sun is a staggering 93 million miles away. When the CME collided with Earth's magnetic field, it unleashed a powerful geomagnetic storm that disturbed our planet's magnetic environment and generated strong currents in the ground. The telegraph lines, which were vital for global communication at the time, experienced severe disruptions. Sparks erupted from telegraph machines. Operators received electric shocks, and some stations even caught fire. The induced currents were so strong that operators were able to send and receive messages even after disconnecting their batteries. This incredible event not only demonstrated the power of solar activity, but also revealed just how interconnected we are with our sun. The Carrington event was not just a historical milestone, it also produced a breathtaking display of auroras that dazzled observers across the globe. These stunning light shows were so vivid and widespread that they extended far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported witnessing the sky illuminated with vibrant colors. The auroras were so intense that they transformed the night sky into a brilliant canvas, allowing folks in the northeastern U.S. to read newspapers by their ethereal glow. In the Rocky Mountains, gold miners were even roused from their slumber, mistaking the dazzling light for dawn and beginning to prepare breakfast. Witnesses described the sky as glowing with radiant hues of red, green, and purple, swirling majestically across the horizon. Now, imagine if a solar storm of the magnitude of the Carrington event were to strike Earth today. The consequences would be catastrophic. Currently, the Sun is undergoing a significant transformation, specifically the reversal of its magnetic field, a phenomenon that occurs approximately every 11 years as part of the solar cycle. This magnetic shift, driven by the solar dynamo, could have extensive effects on Earth, potentially leading to disruptions and disasters. The Sun's magnetic field is generated by the movement of electrically charged gases within it, creating a complex and dynamic magnetic environment. As we move forward, it's crucial to understand how these solar activities could impact our planet and our way of life. At the heart of the Sun's dynamic nature is a complex structure that ultimately leads to the reversal of its magnetic poles. Composed primarily of hydrogen and helium plasma, the Sun generates energy through nuclear fusion in its core. This energy then travels outward, first through the radiative zone and then by convection in the outer layers. The solar dynamo system, which operates within the convective zone and a crucial thin layer known as the T-line, is responsible for generating the Sun's magnetic field. One fascinating aspect of this process is differential rotation. The equator spins faster than the poles, stretching and amplifying the magnetic field lines and driving the solar cycle. Currently, the Sun is in its solar maximum phase, where sunspots and solar activity reach their peak. This heightened activity can lead to potential risks, including solar flares and coronal mass ejections, (CMES), which can disrupt satellite communications, affect power grids, and pose dangers to astronauts in space. To stay ahead of these potential hazards, scientists closely monitor the Sun's magnetic activity and sunspot behavior to predict when magnetic field reversals might occur. Sunspots arise from tangled magnetic lines and can produce solar flares and CMES, massive bursts of energy that impact Earth in various ways. While solar flares release intense radiation, CMES eject substantial amounts of solar particles into space. These phenomena can enhance the beauty of auroras, but also bring serious risks that require our attention and preparation. The Sun's behavior presents significant threats to Earth's technology and infrastructure, showcasing a captivating interplay of physics and natural events that influenced not only our solar system, but also life on our planet. Understanding the complexities of solar activity is crucial, especially as we grow more reliant on technology that can be impacted by these solar events. The Sun generates energy through nuclear fusion, a process that converts hydrogen into helium, while releasing enormous amounts of energy. This energy then travels through the different layers of the Sun before finally reaching the surface and radiating out into space. Solar activity manifests in several forms, including sunspots, solar flares, and coronal mass ejections. CMES sunspots are cooler regions on the Sun's surface caused by magnetic activity, appearing as dark spots against the brighter backdrop. Changes in solar activity follow an approximately 11-year cycle, known as the solar cycle, where phases of high activity, called solar maximum, are followed by calmer periods known as solar minimum. During the solar maximum, the number of sunspots increases, leading to a higher frequency of solar flares and CMES. Solar flares are sudden bursts of energy that release radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense eruptions can disrupt satellite operations, navigation systems, and even power grids here on Earth, emphasizing the importance of monitoring solar activity as we navigate our technology-dependent world. Solar activity can disrupt radio communications and pose serious risks to astronauts in space. But what about coronal mass ejections? CMES, these massive eruptions of solar wind and magnetic fields burst forth from the solar corona and are hurled into space. When directed toward Earth, CMES can trigger geomagnetic storms that disrupt our planet's magnetic field. While they create stunning displays of auroras, they can also lead to significant interruptions in our technology. The effects of solar activity extend far beyond the cosmos. They reach deep into Earth's atmosphere and surface. Research shows that fluctuations in solar radiation can influence climate patterns, potentially contributing to unusual weather events. Increased solar activity can also lead to warming in the atmosphere, a crucial factor in discussions about climate change. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.